Your GPU is lying to you. Right now, if you have a graphics card running inside your machine, it is almost certainly operating at temperatures that would alarm most users. Somewhere between 83 and 90 degrees Celsius under a full gaming load. And if you have ever watched a temperature monitoring tool and felt that spike of anxiety, wondering whether something is wrong, whether your system is failing, whether you need better cooling, you have been manipulated, not by your hardware, by a story about your hardware that the industry has never really bothered to correct. Because here's what the engineers actually know, and what almost nobody in consumer technology content has ever explained properly. Those temperatures aren't a sign of inadequate cooling. They are the target. They are the design goal. And the reasons why are rooted in semiconductor physics that are frankly counterintuitive enough to make you question everything you thought you understood about how modern chips work. This is the science of GPU thermals. And almost everything the mainstream conversation gets wrong about it. Let's start at the foundation, because to understand why your graphics card runs hot on purpose, you need to understand something that sounds almost paradoxical when you first encounter it. Transistors, the billions of microscopic switches that make up a modern graphics processing unit, or GPU, do not all behave the same way at all temperatures. There is a phenomenon studied extensively in microelectronics research, documented in publications like the Microelectronics Journal, called hot carrier velocity saturation reversal. The name is dense, but the concept is important. At very low temperatures, certain performance characteristics of silicon transistors actually degrade. There is a thermal sweet spot, a range in which the physics of electron movement through the silicon lattice becomes more favorable. NVIDIA's own thermal design white papers for their RTX 30 series products, published in 2020, make this explicit. They state a performance headroom temperature target of 83 degrees Celsius, not a thermal ceiling to be avoided, a performance target to be hit. What this means in practice is that chip architects at companies like NVIDIA and AMD are not designing cooling solutions to keep temperatures as low as physically possible. They're designing them to hold the die at a specific operating temperature, warm enough to extract optimal clock behavior from the silicon, but below the threshold where heat becomes genuinely destructive. The consumer narrative around GPU temperatures, that cooler is always better, that hitting 85 degrees means something has gone wrong, is simply not how the engineering works. This reframes the entire conversation. When you see your GPU sitting at 88 degrees and your fan curve is responding accordingly, you are not witnessing a system under stress. You're witnessing a system doing exactly what was asked of it. But here is where it gets considerably more interesting, and where a misconception even more pervasive than the temperature. One has been quietly misleading millions of PC enthusiasts for years. Most people who monitor their hardware have encountered the term thermal throttling. ETs discussed constantly in benchmark videos, in forum threads, in product reviews. And the assumption is almost universal. If your GPU is throttling, it is because it is too hot, and better cooling is the solution. This is wrong in the majority of cases, and the error is not a small one. GPU manufacturers, and this is documented in technical analysis by Igor Walasek, at Igor Walasek, cross-referenced with AMD's own RDNA, 2 power management documentation published on GPOpen, actually differentiate between several distinct types of clock reduction. There is thermal throttling, which is a direct response to die temperature. There is power throttling, which reduces clocks to keep the card within its total design power, or TDP envelope. And there is current throttling, which protects the voltage regulation circuitry on the card itself. These are separate mechanisms with separate triggers. They are not equivalent. The critical finding, and this is the one that should change how enthusiasts approach their hardware, is that in most real-world gaming scenarios, the clock speed reduction that users observe and label as throttling is almost entirely power throttling, not thermal throttling. The card is hitting a power budget limit, not a temperature limit. Those are fundamentally different problems, and power throttling cannot be solved by better airflow, a higher-end cooler, or cleaning out your case. No amount of thermal improvement addresses a power budget constraint. The chip simply needs more watts than the manufacturer has allowed it to consume, and no heatsink in the world changes that. This means that a significant portion of the aftermarket cooling industry, the thermal pads, the cooler replacements, the elaborate case airflow configurations that enthusiasts invest real money into, is solving a problem that does not exist in the system they are applying it to. The performance impact, measured carefully, is frequently zero, not marginal, zero. Now, this does not mean cooling is irrelevant. There are absolutely situations where thermal throttling does occur, and where improved cooling has a genuine measurable impact. But the point is that most users cannot distinguish which mechanism is limiting their hardware, and the industry has never done a particularly thorough job of explaining the difference. It is, in that sense, a very convenient ambiguity. Let's stay with thermal realities for a moment, but move to a different platform. One where the situation is considerably more acute, and where the physics of degradation are genuinely alarming. Once you understand laptop thermal compounds. This is a subject that should be discussed far more than it is. When a major manufacturer, Dell, Asus, others, assembles a laptop at the factory, they apply thermal paste between the processor die and the heat sink assembly. This paste is the critical thermal interface material. It fills microscopic air gaps in the metal surfaces and allows heat to conduct efficiently from the chip to the cooler. The paste they use is functional. At the time of manufacture, it works. The problem is what happens over the following 18 to 24 months of normal use. Independent teardown analysis from Notebook Check, supported by research published in the Journal of Electronic Packaging from the American Society of Mechanical Engineers, has documented something that desktop PC users almost never have to consider. Laptop thermal paste degrades to less than 30% of its original thermal conductivity within roughly 2 years. Meanwhile, the same thermal compound applied to a stationary desktop system retains over 85% conductivity after 36 months. The reason is mechanical. Every time you put a laptop in a bag and carry it somewhere, the chassis flexes slightly. Every time IT is placed on an uneven surface, moved, jostled. The contact interface between the heatsink and the die experiences tiny stress cycles. Over hundreds and thousands of these microcompressions, the paste matrix, which is not a solid material but a suspension of thermally conductive particles in a carrier medium, develops microfractures. The particle network that conducts heat breaks down structurally. And this process simply does not happen in a stationary desktop, where the thermal interface sits undisturbed. The practical implication is this. If you own a laptop that is more than 2 years old, the thermal paste between its processor and its cooler is very likely operating at less than a third of its original effective. The performance and temperature behavior you're experiencing today is not representative of that hardware's capabilities. A repaste, a procedure that costs very little in materials and can be performed with modest technical skill, would, in a genuine thermal throttling scenario on a laptop, make a larger difference than almost any other hardware-level intervention available to a consumer. But this is almost never discussed in mainstream content, because it is not a product anyone can sell you. The degradation is invisible. There is no warning. The system doesn't tell you the paste is failing. It simply runs hotter and clocks lower, and most users conclude the hardware is aging out naturally. Now there is a related myth worth examining, one that has accumulated near religious status in PC building culture. And the data behind it is considerably less flattering to the ritual than most people expect. Dust cleaning. The idea that regularly removing dust from your PC's fans and heatsink fins is essential thermal maintenance is one of the most widely held beliefs in the enthusiast community. It's advice given constantly, treated as obvious, and almost never questioned. The reality, according to a study examining 120 consumer PC systems, is considerably more nuanced. The study, conducted by Hardware Unboxed and cross-referenced with technical notes from the Cooling Technologies Research Center at Purdue University, found that 67% of measured systems showed less than 1.5 degrees Celsius temperature difference before and after a full cleaning. 67%. The reason comes down to a threshold effect. Dust accumulation only begins to meaningfully impede airflow through heat sink fins once the layer exceeds approximately 2 millimeters in thickness. Most home-built systems in environments without carpets or pets don't reach that threshold even after 2 years of operation. This does not mean you should never clean your PC. There are real scenarios where dust is genuinely problematic. High particulate environments, carpeted floors, systems with pets in the household. But for the majority of users following the ritual of quarterly cleaning with a sense of dutiful necessity, the thermal benefit is statistically negligible. The cleaning has become a form of psychological maintenance, a way of feeling like you are taking care of your hardware, rather than a thermally meaningful intervention. The counterintuitive finding is that the users most likely to clean obsessively are probably the ones least likely to actually need it. People who build clean, carefully managed systems in well-ventilated rooms are dusting components that weren't meaningfully dirty to begin with. There is something happening in memory systems that almost no consumer content addresses, and it sits in a space most users don't think about at all. The intersection of temperature and data integrity. DDR5 memory, the current high-performance standard used in modern systems on both Intel and AMD platforms, has a documented thermal sensitivity that is codified in the JEDEC standard JESD 795B. The formal specification document that defines how DDR5 operates. Specifically, Section 4.9 of that standard defines a mechanism called temperature-compensated self-refresh, which acknowledges something fundamental. DRAM cells leak electrical charge over time, and the rate of leakage increases with temperature. When leakage outpaces the memory's self-refresh cycle, which operates on a 32 millisecond interval at standard settings, the stored data bit becomes uncertain. The error-correcting circuitry built into DDR5 catches most of these events. They are logged as correctable errors. The data is recovered. The system continues operating. Academic research, specifically a landmark study titled DRAM Errors in the Wild by Schroeder, Pinheiro, and Weber, published through the ACM Special Interest Group on Measurement and Evaluation of Computing Systems, Sigmetrics, in 2009, found that error rates effectively double for every 5 degrees Celsius increase in operating temperature above 45 degrees Celsius. Above 45 degrees, which is a threshold that DDR5 modules running in an enthusiast system, particularly in a compact case with aggressive memory overclocking settings, can approach or exceed under sustained load. Here's the part that should give you pause. Consumer motherboards based on Intel Z790 and AMD X670 chipsets do not surface these correctable errors to the user in any accessible way. There is no notification. There is no log entry that most users will ever encounter. The error correction happens silently, thousands of times per second in affected systems, with the user entirely unaware that their memory is operating in a regime where data integrity is being actively maintained by error correction hardware rather than by clean electrical margin. The system is not failing, but it is working harder than it should have to. And most users running high-performance memory configurations have no idea this dynamic exists at all. Now let's talk about something that sits at the other extreme of the DIY enthusiasm spectrum. A product category that has been aggressively marketed to the most technically engaged users in the PC building community, and where the long-term reality is almost the inverse of the marketing. Liquid metal thermal compounds. These are products, often gallium-based alloys, marketed as the ultimate solution for CPU and GPU temperatures. They have genuinely exceptional thermal conductivity. On paper, and in the short term, they deliver on that promise. Temperature reductions of 10 to 15 degrees over high-quality conventional paste are documented in controlled conditions. For enthusiasts pushing silicon to its absolute limits, that headroom matters. The problem is the 6 to 8 week Mark. Thermal Grizzly, one of the primary manufacturers of consumer liquid metal compounds, includes in their own application guidelines an explicit warning against use with aluminium heat-sink surfaces. The reason is electrochemical. Gallium, the primary active component of liquid metal thermal compounds, reacts with aluminium to form an alloy at the contact interface. As that interface is exposed to the oxidizing environment of a running system, aluminium gallium oxide forms progressively at the contact surface. Research published in the Journal of Applied Physics, Volume 127, in 2020, quantified both the formation timeline and the consequence. The oxide layer that develops within 6 to 8 weeks of application has a thermal conductivity approximately 40 times lower than the liquid metal itself. 40 times lower. What this means in practice is that an enthusiast who applied liquid metal to a heatsink with an aluminium contact surface, which is a large number of common consumer coolers including some popular and well-regarded models, and did so without a nickel-plated interface, which is the required protection against this reaction, may now be running with a thermal interface that performs significantly worse than if they had simply used the degradation is invisible. The oxide layer cannot be seen without disassembly, and the performance loss accumulates gradually enough that the user never notices a sudden change. It is, in a genuine sense, an expertise trap. The users who sought out the most advanced thermal solution available were rewarded over time with worse outcomes than the users who chose the straightforward option. There is one final piece of this puzzle that reframes almost everything said so far, and it concerns the direction the industry is moving, rather than where it has been. The conventional assumption about heat and power in computing is simple. More watts means more heat, and chips with lower power consumption run cooler and are easier to manage thermally. This is broadly true at a system level, but at the die level, the scale of individual chip packages, the relationship is becoming significantly more complicated, and the implications will affect every consumer who buys high-end hardware over the next several years. At the Taiwan Semiconductor Manufacturing Company's, or TSMC's, Technology Symposium in 2022, engineers presented findings on what they call thermal density challenges in sub-5 nanometer process nodes. The core finding is this: as transistor density increases with each process node advancement, moving from 7 nanometer to 5 nanometer to 4 nanometer fabrication, the same number of watts is being generated in a progressively smaller physical area. The die shrinks, the transistors pack more tightly, the heat source becomes more concentrated. Analysis of NVIDIA's ADA Lovelace architecture, manufactured on TSMC's 4 nanometer process, showed that hotspot behavior, localized regions of extreme temperature within a 2 to 4 square millimeter area of the die, occurs with greater intensity than in the previous Ampere architecture, despite Ada Lovelace having competitive or in some configurations lower overall. The consequence is counterintuitive and important. A chip with a lower total design power number on the specification sheet can be harder to cool effectively than its higher TDP predecessor, because the heat is concentrated in a smaller region, and the average temperature, measured across the die, does not capture the localized extremes. Cooling solutions designed and validated for previous generations may not transfer their effectiveness to newer architectures in the ways users expect. The hotspot throttling that affects those 2 to 4 square millimeter regions can limit performance while the rest of the chip remains well within comfortable operating ranges. And standard temperature monitoring tools, which report averages, may not reveal that the constraint is even occurring. This is where thermal engineering for consumer hardware is heading, and the gap between what the marketing materials describe and what the physics actually demands is going to widen as node shrinks continue. What ties all of this together is not a simple narrative about industry deception or manufacturer incompetence. The picture is more nuanced than that. GPU engineers designing for a target operating temperature of 83 degrees are making a legitimate engineering trade-off, one that the physics of silicon actually supports. The distinction between power throttling and thermal throttling is real and meaningful, and the fact that It's rarely explained clearly, is more a failure of consumer content than of manufacturer transparency. Laptop thermal paste degradation is a genuine and underappreciated problem, but it stems from the mechanical realities of portable hardware rather than any deliberate corner cutting. And the liquid metal situation is, if anything, a story about the dangers of enthusiast knowledge outpacing enthusiast context. The deeper pattern here is about the gap between the model most users carry in their heads and the actual behavior of the hardware they are running. That gap is not random. It follows a consistent shape. The popular mental model of how thermals work is simpler, more intuitive, and more action-oriented than the engineering reality. Cooler is always better. Throttling means overheating. Dust is always the enemy. Liquid metal is always superior. These heuristics are easy to remember and satisfying to act on. They are also, in specific and important ways, wrong. Understanding the actual physics doesn't mean abandoning good practices. It means applying them where they actually matter rather than performing maintenance theater on hardware that doesn't need it while missing the interventions, like a laptop repaste or understanding which throttle type is actually affecting your system. That would make a genuine difference. If you've made it this far, this channel is probably exactly what you were looking for. Every video here goes to the actual research, the technical documentation, the academic studies, the engineering specifications, and translates what's actually known into something that respects your intelligence. If that's the kind of content you want more of, the subscribe button will make sure you don't miss what comes next.